today's talk is about the evolution of neural network architectures in ASR. So we all know that neural nets, especially deep neural nets, are extensively used practically in all the areas of speech technology today. However, neural nets were already used in the early 80s and mid-80s, especially in the ASR. So today, Hervé is going to give us a talk about this progress over the past about 40 years. So I'm not going to spend too much of your time. Ladies and gentlemen, let us welcome Professor Hervé Bourlard.
And first of all, I would like to thank the organizers for setting up such a great conference and inviting me, taking the risk of inviting me to give this plenary talk, since many of them, they know me quite well, so they know that they can expect anything from me today. Okay, so first of all, I have to say that this is a tough talk, right? Very challenging talk to talk about deep neural network these days. There are so many things going on, new breakthroughs basically every week. Right, so I will ask you to forgive me if I forget to list one of the buzzwords or one of those recent breakthroughs. Actually, there are so many breakthroughs that it's very difficult to follow up, right? I just heard, maybe some of you got this message this morning saying that the 20,000 seats of the NIPS 2080s had been sold out in 18 minutes, 30 seconds this morning. So it's worse than a Bob Dylan concert. Wow. That's so great. So this is the title of my talk, very ambitious. Now I have a subtitle which could read like this, also gradient descent through an equals function and any type of deep neural network architecture. Basically that's what we have learned over the last 10 years, I believe. Today we can do gradient descent through any type of architecture, recurrence or no recurrence, multi-layer or not, any cost function, local, global at the sequence level. So the goal of the talk, as I said, I have to speed up a little bit, so I have to squeeze because I had prepared a 1-hour talk, so about 35 slides, and now I was told that my talk should be done by 9:20, so I will skip a few slides, or I will move faster. So I will discuss a little bit about what is known for sure about neural networks and how they can be used for ASR. So I am not going to talk about magic, wizards, and beliefs. I will talk a little bit about the current trends that I believe are important, current challenges, opportunities, and again, as I said, no discussion about latest buzzwords. Actually, I cannot even remember those buzzwords. And people are doing very well and inventing new buzzwords every day. A quick note about, since everybody's talking about recurrent neural nets, a very quick note. There are more and more evidences and papers, and I point you to a very good one recently published by Berkeley people, that most recurrent networks don't need to be recurrent. The famous infinite memory advantage of recurrent neural network is largely absent in practice. This is good to know. And for the oldest people who used to play with filters, filter design when they were young, I'm sure there are still a few of them in the room, I invite you to take this little exercise. You take a stable, infinite impulse response filter, IIR filter, xn at the input, yn at the output. So you have there the equation of the simplest IIR filter that I can think of. If you want to simplify it further, you take capital N equal 1, so you are left with one parameter B, and then you do M equal 1, so you are left with a second parameter A, so you have two parameters. You can try to design that filter to be stable. For people who play with those filters, they know that it's already a major challenge to make those filters stable. But suppose you have found one that is stable, so you generate x's and y's, then you forget about the filter, and I invite all of you to try. It's a very interesting exercise for a master student. I invite all of you to attempt to train the two parameters, A and B, by backpropagation. It will be a lot of fun. Tell me if you get if you converge to the optimal solution. Okay? So I have some doubts sometimes about recurrences. It's very difficult to understand what's going on in recurrences, right? And when I see how difficult it is to train two parameters in a simple, linear recurrent system, I think we should ask ourselves what we are doing with nonlinear recurrent systems. Anyway, let's be a little bit more serious. So what's going on today in speech recognition? So we have feature extraction as usual. There is some work, DNN work going on, trying to expand context, model a convolutional neural network, trying to build end-to-end system, whatever that means. I'll come back to that later. Try to do autoencoder. I am trying to adapt to the lexicon all the time. So auto-associative neural network, autoencoders, and I think they have other names. Stacked autoencoders, denoising autoencoders. So this is all the same, but that comes at the feature extraction level. At the acoustic model, that's where there is most work going on these days, right? A lot of DNN work, recurrent neural network, convolutional neural network, LSTM, TDNN, tuning, backpropagations, playing with different non-linearities, ReLU, sigmoids, softmax, linear, and so on. Different, max pooling is another nonlinear function and so on. So playing with all of them, most of the time people don't understand why they do it, so they have a big mix of all those things. And then they try many hidden layers and they see which one works better. Okay? Language model, there is a little bit going on there, although there are more and more papers showing that finally n-grams are damn good. They are really hard to beat. So even recurrent neural network for language models or TDNN, which tend to be better than recurrent neural network these days, they are still not doing better than n-grams. So, the usual trick for scientists like us is to mix the two, merge the two models, and then sometimes you get a slight advantage. Not much at the lexicon level, not much at the decoder itself, besides what is called the CTC, which is sometimes considered as a poor ersatz of alpha-beta recursions that I will talk about very quickly. By the way, I will have 2 slides with equations. If you know those equations, you don't have to pay attention because you know them. If you don't know the equations, don't pay attention, you will not understand them, but this will not prevent you from understanding the talk anyway. Okay? So first I want to start with Markov models, which has been there since 1975, more or less. So Markov model, stochastic finite state automaton, sequence of states, states modeled by Gaussians, multi-Gaussians, and more recently, or in the mid-80s, by neural network outputs, multi-layer perceptron at that time. So we have a sequence of input vectors, capital X, written as x1t. We have emission probabilities, P of xt given qk, and transition probabilities to go from one state to another one. That's my survey, HMM survey. So most of those HMM, as well as DNN today, they are dealing with context-dependent forms. Now it's more like CNOM, called CNOMs. So CNOMs are context-dependent forms where they depend more than just context. So they depend on many more parameters than context. So we can have up between a few thousands to a few tens of thousands of those CNOMs. So this is the number of hidden Markov models or the number of DNN outputs. The words are defined as a sequence of those forms or CNOMs. Lexical model is there to accommodate inter-speaker variability in theory, is there to accommodate multiple pronunciation models, and we know for many years that that model can be acquired from linguistics. So prior information, this is a word I will pronounce many times, prior. Or they can be learned from data, which means from other priors. Linguistics or us, when we draw an HMM architecture, we set up the priors. Even without looking at the data, as soon as you have drawn a 3-state Markov model with transition probabilities, nothing else, I know the prior probability of P of qk. You have to believe me, right? If I look at data used to train a neural network, there is prior also included in the data itself. And there is no way on earth to have those 2 priors being equal. So we will have to decide which one do we get rid of. We will come back to that later. First order Markov model, but usually that's not a problem for any of us, since we know that any high order Markov models can be approximated as a slightly more complex first order Markov model. And a sentence is a sequence of words, n-grams, so which is an nth order Markov model. Okay, this is my first equation slide that speech people know very well. You will find the same equations in CTC, except that to confuse people, they will add a blank symbol and a few other fancy things. Blank symbols were already there at IBM in the 70s, by the way. They were calling it an empty symbol. But these are the alpha recurrences. Very important. Alpha recursion, beta recursion. Again, I'm not going to discuss the equations, but that's a way to compute the likelihood of observing a vector xt at time t on a particular state qt at time, and particular state qi at time t. So this is a recurrence, right? If you replace the sum by the max, you get vector b and so on and so on. Backward, same thing. Backward. I'm going to skip the equation, but what you have to understand is the gamma, which is often called the gamma posterior. This is an important value for all of us doing HMM or neural networks. You have to keep that value in mind all the time. So the gamma is a gamma posterior. It gives you the probability to be in state qi at time t, given the whole acoustic sequence, looking at everything. So it's better than a recurrent neural network. I look at the entire sequence, and I can do it. And there is an equation to do that. And you get a posterior probability of a state given the entire sequence. And in P of qti, if I happens to be a final state of a word, you get the posterior probability of a word given the entire observation sequence. That's interesting. I'll come back to that later. So now we are moving from HMM to deep neural networks. So why do we do it these days? Why we are doing it already in the mid-80s? Because according to Fred Jelinek, and I agree with him, of course, well, it's quite probable that I'm citing him here, that HMM are like the wheel, the building crane, or silicon, all perfect machines for their task. Actually, even Shannon laid down the foundation of information theory around HMM. HMM are very powerful. We shouldn't get rid of them just for fun and just say, oh, I don't want to understand HMM, let's do DNN. You know? So what are the most important charges against HMM? There are not so many of them. The biggest one is in bigger fonts, and then there are two others that can be circumvented in different ways. The biggest one is the famous conditional independence assumption of the output, right? So the acoustic vectors within a state are independent of each other, are not correlated, and they are also independent of the previous state. So this is the key assumption that we want to fight, we want to fix if we do something else than HMM. The second charge could be HMM are not discriminant. They are generative models, but there is nothing really wrong with generative models, actually. They have different properties, but if you have infinite amount of data, both of them are going to converge to the same solution. Whether it's generative model or discriminant model, they both converge to the same solution, assuming you have an infinite amount of training data. Of course, infinite is a large number, right? And we never have such a large number, so we have to keep it in mind. Another thing which explains what we call the fudge factor in speech recognition, the acoustic and language model are trained independently of each other. So I think there will be, I haven't seen anything yet, but there may be some trend towards better integration of language modeling and acoustic modeling using maybe deep neural networks. So when we do deep neural network, that's the way I use them. I try to understand what I'm trying to fix. Because if it is not broken, you know, I don't want to fix it with something which is even more broken, called DNN, or even worse, recurrent neural network. I'm sure I'm not going to please everybody here in the room, but I take responsibility for what I say. Okay, so 1988, so I think we were among the very first one with colleagues and in different places, and including Berkeley certainly, to just show you know, by mistake. We were lucky to show that if we have a neural network at that time called MLP, multi-layer perceptron, trained along several criteria, but there are many more of them. So least mean square, entropy, relative entropy, and many more. If you do it properly, you know, if you do proper cross-validation, one leave one out, and fold cross-validation. Sometimes I think they call it differently. Oh yeah, dropout. If you do dropout, this is another regularization technique, so there are many of them. So if you do it properly, you are going to generate a very good estimate. I'll show you what I mean by very good estimate of posteriors, of output classes given the input. And neural networks, they can accommodate a lot of inputs. So in that case, we are accommodating left and right context at time t, around time t. At that time, and still today, people are using 90 frames. 4 frames on the left, 4 frames on the right, the center frame. Since we have more and more data, people try to use larger context. Most of the time it fails for other reasons that have nothing to do with the size of the data. Okay. So when we got that, you know, my friend Morgan in Berkeley and I, we struggled for months, you know, and because the results were not very good. Actually, there is something fun with speech recognition, and I can see that in all the papers these days. For people who have been working half of their life on speech recognition, there is something we know for sure. It's very hard, and I see John there, so he's going to agree with me, I'm sure. It's very hard to improve an excellent baseline system on a very difficult task, right? It's very, very hard. Now, surprisingly, it's also very hard to damage it very much when you do something very wrong. So you can still get something close enough to the baseline, so you damage your system completely. You break it by using all kinds of funny ideas, you know. You break it, but you can still write papers because you are not too far from the baseline system. So that's what it's funny with speech recognition, right? It's really hard to improve, but it's also very hard to damage it very badly. That's good. So in our case, we were also damaging the recognizer, although we had a good theory. Then it took us some time to realize that we had to divide by those priors by those posteriors on your left side, right side, by the priors as observed on the training data. And we were getting something that we call scaled likelihood, which was interesting because it's solving several problems at the time. Not only the neural network is discriminant, but I like to work with scaled likelihood. The problem with likelihood is that it's dimensional. If you increase the size of the xt, the observation vector, you change the value of the likelihood. You go from 10 minus 33 to 10 minus 65. Likelihoods are dimensional, so you have to retrain the fudge factor and many other things in your system. If you have scaled likelihood is not dimensional anymore. It behaves much better. And this comes in addition to several other advantages. So we don't make any assumptions about the underlying probability density function like we were doing with Gaussians, multi-Gaussians. We model partial context. We take context into account partially. So we are not expecting to do as well as RNN, modeling infinite memory. We have discriminant training at the local level, and this is something that will come later in my talk where there is a potential. They generalize surprisingly well, and with quite few parameters. So that's interesting, right? So when I say a neural network are good estimates of posteriors, I show you this thing. You may have seen it. It's one of our first book in 1994. So there are people who understand it, people who don't understand it. But that's very easy to understand this plot. If you have a posterior estimate in a black box, that's the best way to estimate, to see whether your posterior estimate is a good posterior estimate. So I do there, on the x-axis, I plot the neural network output yielding the maximum output, so the classification. So I plot my maximum output of the neural network. I put them into bins, I discretize them, I put them into bins between 0 and 1, because those numbers are between 0 and 1. You know, and on the y-axis, so I get, in every bin I have many of those vectors, right? Values. All the input vectors yielding an output of 0.4, let's say, with maximum probability. And I have millions of them in each bins. And for each bins, I also check how many times those vectors yielding 0.4 as maximum classification was properly classified. So if we have a base classifier, that value 0.4 should be equal to the number of correct classification. Because the number, the posterior probability is also a number of the confidence level. Right? So in theory, we should be as close as possible to the diagonal. When I showed that to Fred Jelinek many years ago, he said, oh, that's great, you know. So let's add another layer to try to squeeze something that is not yet along the diagonal to the diagonal. And he was right, but I was too lazy, I never did it. Or maybe I didn't have enough students around at that time to do it for me. Okay, but this is very important. And you will see a second plot very similar to this one in 2 minutes. This is going to be very tough to finish in 9:20, but okay. A few selected implications. Once we understand that, I think I can speed up a little bit. Posterior input, they include training data class priors. I said it already. Those priors are not uniform. There are people trying to balance those priors into training data. Don't do that. So there is a conflict between training data priors and HMM state priors, which is to be resolved. There are 3 ways to resolve them. I don't have time to discuss it. You get rid of one, or you get rid of the HMM priors, you get rid of the data prior, or you try to reconcile both in a smart way. Output bias. If you know that the output of your neural network is a posterior probability, you have a nonlinear function at the output, you can see what's going on before the nonlinear function. So you compute it, you invert the nonlinear function at the output, and then you factor out what depends of the input and what is independent of the input. You factor it out, and basically what doesn't depend on the input is called the bias. It's the bias of the neural network output unit. And the bias, in the case of a sigmoid or softmax, turns out to be bk is equal to minus log p of qk divided by 1 minus p of qk, which in statistics is called the log odds. Very interesting value. So when you train a neural network like that, try to initialize your bias with that value. Your weights usually are going to be kind of 0001 or 002. The biases usually are values like 6. Take a p of qk equal 1, so 0.1 divided by 0.9. Take the log, minus log, 6. And it will take you forever to train those outputs. So just initialize the biases properly right at the beginning. It will save time, and you don't have to do those fancy things that some people are doing. Okay, you remember those alpha-beta recursions? So assuming you understood it, what is nice is that once you understand the scaled likelihood trick, so we divide the output of the neural net by priors, we get scaled likelihood. Well, all those alpha and beta recursions, they still hold perfectly. So I can write an alpha recursion with scaled likelihoods. It's perfectly correct. That equation is perfectly correct. Everything remains the same. Except that this equation behaves much better because I have scaled likelihood. I don't have underflow problem. Everything behaves very well. Okay? And as we were doing, if I look at the last state of a word, I can also compute the gamma, the scaled gamma S, IT. So this is again another value of the gamma posterior, the posterior probability of a state given the entire sequence. Interestingly enough, I don't want to swamp you with more equations, but once you understand that, you can also do it hierarchically. So P of qti given x1t there, so this is the posterior probability of a state given the whole sequence. That state could be a final state of a word. So by looking at all those gammas over all the final states, you have a posterior distribution taking all your sequence into account. You have a posterior distribution for all the words. And you can send it to a higher level decoding system. Or to a smart language model maybe, doing something slightly better than n-grams. We can look at full posterior distribution over the words. Very interesting. But I don't have time to develop that further here. Okay, but if once we understood that, we can do what we do in HMM for decades. We can do this EM training of any types of neural network. So these days, I think many people, they call it end-to-end systems. Although it keeps changing names all the time, but the most frequent name I see is end-to-end system. When they, oh yeah, flat start, end-to-end system, something like that I see. But basically, so you train, flat start means that you train the neural net from scratch, or you start with a segmentation coming from a GMM or whatever. These are details. But you can train an HMM, then you do the E step. E step you are going to compute. So from the gamma posterior that I just told you, you can compute the posterior distributions of every state, QK, given the entire sequence and the parameters. Wow, that's good. And given that, you can go to the M step. You can re-estimate the parameters to maximize the likelihood, or the posterior, depending on your cost function. Right? So here, the first equation requires forward-backward, the regular one, or the scaled forward-backward. The second one requires training neural network. So the big difference between what we are doing today and what we were doing with HMM and Gaussians is that with Gaussians, it's also a gradient descent, except that at every M step, we take the optimal gradient because we can define an auxiliary function. It's called an auxiliary function which is convex and which we can maximize in one step. So it's a gradient descent where we compute the best gradient in one shot and we reach the maximum of the auxiliary function in one shot, analytically. There are few neural network cases, depending on the architecture of the deep neural network, where you can do the same thing. So you can define a convex auxiliary function allowing you to train neural network in this way. Okay, so this is just what people call a posteriogram. So this is the one we get from MLP posteriors or neural network posteriors. That's the second one is coming from gamma. So after the processing, the alpha beta smoothing, basically polishing, and you can see that we are getting better gamma posteriors, which we can send further to compute word posteriors and sentence posteriors. Okay? So I'm going to go very quickly on this one because this has been known for a lot of time, 15 years, 20 years. So different ways to use MLPs into HMM, turn posteriors into scaled likelihood, and use them into likelihood-based HMM. Second one, extracting bottleneck features. Somewhere at the middle of the neural network, you have a bottleneck layer, and then you use that as so-called bottleneck features, and you send them to an HMM again. Third system referred to tandem. You use the DNN output, called posteriogram, as HMM features. All of them work very well, and still today I have difficulties to tell which one is good. Well, I think people don't even look at that most of the time. Well, it looks like very often the bottleneck features are performing very well. Recently in the bubble context, the DARPA project, the bottleneck features were doing well. But the tandem features are also doing extremely well, and using the posteriors directly are also doing reasonably well. But anyway, the three solutions are kind of summarized in that plot. If we use the DNN output as features, usually we are going to take the log and do a KL transform before sending that to an HMM, GMM, because GMMs, they prefer Gaussian distributions than posterior distributions. So we are going to normalize them. Okay, that's the end of the past. Let's go. That's going to be interesting. Yeah. 20 minutes, yeah. Time to have fun. Move from MLP to deep neural network. So what is deep neural network? It's a catchy name for MLP with many hidden layers. That's it. That's all what we have to remember. So input, we have context windows of frames. Output, we have CNOME, posterior probability. So again, between a few thousands and a few tens of thousands. My challenge is when I deal with deep neural network is to draw the picture first. You know, I'm really bad at drawing pictures, and that one gave me a very hard time. I suspect I stole it from somewhere actually on the internet. I cannot draw such complex pictures, and so you may have recurrences and so on, but I'm not able to do anything like that. Second challenge is you have to buy much more CPUs and GPUs, and then you have to access and process a lot of data. Okay, architectures, number and size of hidden layers remain highly empirical. You know, I have students coming to me say, oh, I've got the best system here on that task, I have tuned and so on. I say, well, why did you come to that? He said, well, I tried many other solutions. And I asked them, and did you also try on that data? And I said, yeah, but then it's another solution. It's another architecture. I say, okay, you know, but that's where we are today.